So now let's see the next derivation. The next is thermodynamic Maxwell's relation based on H. What is H? H is heat content or enthalpy. H is equal to U plus PV. Or from this, what is dH? dH is equal to du plus PdV plus VdP. From first law of thermodynamics, du plus PdV is dou Q, and from second law, that is equal to TdS. Or we can write dH is equal to TdS plus VdP. Okay, it is from this equation that we are going to derive the next Maxwell's relation. Applying the same principle as before, we keep one of the variables constant and differentiate with respect to the other variable. At constant P, dP is equal to 0 or dH is equal to TdS. Now we have to differentiate with respect to S. At constant P, we get dou H by dou S. At constant P is equal to, what do you get? T into dou S by dou S at constant pressure, that is 1. Dou H by dou S at constant P is equal to T. Now let's differentiate this again with respect to P at constant S. Differentiating with respect to P at constant S. What do you get? Dou squared H by dou P dou S will be equal to dou T by dou P at constant entropy. Okay, now let's do the other thing, that is at constant S, what happens to this equation? At constant S, ds is equal to 0 and hence dH will be equal to VdP. Differentiating with respect to P at constant S, what do you get? Dou H by dou P at constant S is equal to dou V by dou P at constant S. So what do we do now? I made a mistake here. It's dou H by dou P at constant S is equal to what is that? That is equal to V. That is equal to V. Okay. In the second step, we have to differentiate again with respect to S at constant P. Why is that? Initially we kept S constant. Now we have to differentiate with respect to S, keeping the other variable, which is P, constant. So this becomes dou squared H by dou S dou P will be equal to dou V by dou S at constant pressure. Okay. In each step you have to be very careful. You saw the mistake that I made. It's possible to everyone, so you have to be very careful. First differentiate with respect to one variable, keeping the other constant. Only in the next step you will have to differentiate again. Don't do both in the single step. Okay. So now we have dou squared H by dou S dou P is equal to dou V by dou S at constant pressure. According to Euler, what does Euler say? Dou squared H by dou P dou S is equal to dou squared H by dou S dou P. This implies dou T by dou P at constant S will be equal to dou V by dou S at constant pressure. Dou T by dou P at constant P, dou T by dou P at constant S is equal to dou V by dou S at constant pressure. This is the second thermodynamic Maxwell's relation based on the function H. Okay, now let's see the third equation, Maxwell's equation based on the third thermodynamic function, and it is A. What is A? A is equal to, A is Helmholtz free energy and A is defined as U minus Ts. So what is dA? dA is du minus TdS minus SDT. Okay. From the combination of first and second law, we have TdS is equal to du plus PdV. Or from this, what is du minus TdS? That is du minus TdS will be minus PdV. Okay, this implies dA is equal to minus PdV minus SDT. Once you have this equation, we'll do the same procedure that was done the previous times. Okay, what will we do? At constant temperature, what happens? dt becomes equal to 0, or we can write dA is equal to minus PD. Differentiating with respect to V at constant temperature, we can write dou A by dou V at constant temperature will be equal to minus P. So we'll differentiate again. Differentiating again with respect to temperature at constant volume. First, temperature was kept constant. Now, we'll kept volume constant. Dou squared A by dou T dou V will be equal to minus of dou P by dou T at constant volume. Okay. Now, what will we do? We'll keep volume constant. At constant volume, dV is equal to 0. What happens to this equation? dA is equal to, this term becomes 0 minus SDT. Differentiating with respect to temperature at constant volume, we can write dou A by dou T at constant volume is equal to minus S. Now we have to differentiate again, interchanging the variables. Differentiating with respect to, here it's T, now it should be V at constant, here it's V, now it's T. So we can write dou square A by dou V dou T is equal to minus of dou S by dou V at constant temperature. Okay. Now, according to Euler, dou squared A by, A being a state function, dou square A by dou square A by dou T dou V is equal to dou square A by dou V dou T. Okay. Dou square A by dou T dou V is minus dou P by dou T at constant volume. Minus dou P by dou T at constant volume is equal to minus dou A by dou V at constant temperature is minus dou S by dou V at constant temperature. The negative sign cancels out. So we can write dou P by dou T at constant volume is equal to dou S by dou V at constant temperature. Now we have the third thermodynamic Maxwell relation. Okay, the first one was dou T by dou V at constant entropy is minus dou P by dou S at constant volume. The second, dou T by dou P at constant S is equal to dou V by dou S at constant P. The third one, dou P by dou T at constant volume is dou S by dou V at constant temperature. Okay. Sorry. Okay. Now we'll see the final thermodynamic Maxwell relation from G. What is G? Gibbs free energy. G is H minus Ts. dG will be equal to dH minus TdS minus STT. H is U plus PV, or dH is equal to du plus PdV plus VdP, but du plus PdV is TdS, or dH is equal to TdS plus VdP. Okay, now let's substitute in the equation for dG. dG is equal to TdS plus VdP minus TdS minus STT. TdS and TdS cancel out, and what is left is VdP minus STT. dG is equal to VdP minus STT. Now let's do the Maxwell's procedure. I'll do the both steps together, differentiating with respect to P at constant temperature. This equation becomes dou G by dou P at constant temperature is equal to V. Okay, differentiating again with respect to, interchange the variables, T at constant pressure. Dou squared G by dou T dou P is equal to dou V by dou T at constant pressure. Okay, so now we'll do the procedure again, interchanging the variables. dG is equal to VdP minus STT, differentiating with respect to pressure at constant temperature, we get dou G by dou P at constant, that's what we did first. So this is differentiating with respect to T at constant pressure. Interchange the variable. So we'll have dou G by dou T at constant pressure will be equal to minus S. Differentiating again with respect to P at constant temperature. Dou squared G by dou P dou T will be equal to minus dou S by dou P at constant temperature. Now we have dou squared G by dou T dou P and dou squared G by dou P dou T. According to Euler's, what happens? Dou squared G by dou T dou P is equal to dou squared G by dou P dou T. Equating dou V by dou T at constant pressure becomes equal to minus dou S by dou P at constant temperature. Now we have fourth thermodynamic Maxwell's relation. Okay.